since we're talking about functions now, here's a really popular, useful function, and it's known as a polynomial function. Now you're gonna notice that we've already looked at some polynomial functions, some very basic ones. So, for example, a quadratic makes a parabola. This is a specific type of polynomial. There's a cubic function. This sort of makes this S shape, and that's also a polynomial function. And even a linear function that makes a line is also a polynomial function. Because if you look up here, a polynomial function just has coefficients and variables and powers that are written in descending order. So you can see here we start with the highest power, and then we decrease by 1, 2, 3, all the way down till we get to x squared, x to the 1 power, and then a constant. And that's normally how you would write a polynomial function. Some terminology that we're going to get to is when you look at this term, which is normally known as the leading term, it's usually written in front. But the idea of the leading term is not so much that it's in front, it's because it has the largest power in the polynomial. There's going to be various powers in that polynomial, but the leading term has the largest. So it could be written in the middle or in the back. It is just formally it's written in descending order, but you look for the largest power, and that is going to help you find your leading term. Now the term that has no power, has no variable, no power, it's just a number, this is known as our constant term. Sometimes will be called a constant coefficient as well. But more than not, we'll call it a constant term. And then there's the leading term. That's going to be really important when it comes to graphing these polynomial functions. Another thing is that largest power can also give you the degree of a polynomial. So the degree is telling you the largest power of that polynomial. And that's going to be useful when we do a couple things. Like here, if you can recognize, the largest power here is 2, 3, and then the largest one is here is 1. And if you notice, I wrote them this way. If you notice, I didn't go 1, 2, 3. And that's because if you look at a quadratic, it points upward, where a cubic points up and down, so does a linear point up and down. And that has to do because the degree of these two are odd numbers. The degree here is an even number. And that's going to dictate how this polynomial function is going to look. And part of how it's going to look is going to be that it does have a lot of these intersecting points with the x-axis. And if you remember, points on the x-axis are known as x-intercepts. And what's an x-intercept? It has a number for our x, right? But because it's on the x-axis, that means it doesn't go up or down at all. That's why the y value is 0. And remember, the y value in this situation is our p of x. And we're going to talk about why we need that later. Or I'll tell you right now that that's what we're going to use as, we're going to call this our 0. So instead of saying find our x-intercepts, we're going to be saying zeros is going to be the term that gets used. Which the 0 just means that your y value is 0. And then you find a value for your x, which that makes x-intercepts. But in this section, we're calling them zeros. And instead of saying y being 0, because we're talking about function, we say p of x, because this is again, function notation. So switching it up. And then there will be this piece about multiplicity, which we will talk about later. But for now, polynomial functions, if you look at just these three, they have these curly movements to them. And a big part of a polynomial function is, one, being able to find your zeros. Two, understanding the end behavior of a polynomial. So looking back at these three, if you notice, when the degree, so remember we said the largest power in the polynomial, when it's even, you're going to have the ends point in the same direction. They might both point up or they might both point down. Now what happens in between, we're going to have to figure out, and that's going to be dictated by our multiplicity, but we'll get to that a little later. And the notation I'm showing here, now if you notice, I'm talking about this a sub n, and that is also has a name, and it's known as a leading coefficient. Since this is the leading term, this is the coefficient for that leading term. That's why they call it the leading coefficient. And that dictates if it's bigger than 0, meaning in other words, if it's positive, right? That's essentially what they're saying. It's saying it's positive. The end behavior of a polynomial is that they're both going to point up. If it's less than 0, that means it's negative. They're going to both point down. And here are just some notations or describing what I said more mathematically. So as x goes, as in other words, we're saying as we go look further in the negative infinity direction, our function, our y values, approach positive infinity. If you notice, as we go further to the right, this is going up, 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 and up. As we go to, as x values, we go towards positive infinity, our y values also go to positive infinity. And that's what this notation is saying. As x is approaching negative infinity, meaning as we go further left, our y values are approaching negative infinity for the y-axis. As x approaches positive infinity, then it points downward, going to negative infinity, the y values. Just kind of just illustrating or writing that in more mathematical terms. And that's because, once again, if you have an even degree, that's the outcome. Now look, for odd, you have this one that points up and down. They point in opposite directions. Hence, when the degree, so I said here, the degree determines the end behavior, and that's the largest power. When it's odd and the leading coefficient is positive, it is up on the right side, but down on the left side. So as x approaches in negative infinity, y goes to negative infinity as well. But as x approaches positive infinity, y also approaches positive infinity. But now, when the degree is odd and the leading coefficient is negative, right, less than 0, it's negative. On the left side, it's going to go up, and on the right side, it goes down, and that's illustrated by this notation. Again, this is just to kind of give us sort of an idea of how these things work. But I'm also going to give you sort of a step-by-step process on how you would graph these, because there's a little bit that goes into it. So to start, we say we have to find all our zeros, which we said a 0 is just because the y value is 0, but we're finding values for x. And those are essentially our x-intercepts. And how do we do that? We set our function equal to 0, and we can solve through factoring, quadratic formula, or on the next video, we'll talk about synthetic division. Once you find those intercepts /zeros, we're going to plot them on a graph. And the moment you're given the example, you can determine your end behavior. And then we're going to talk about multiplicity, which I guess I can talk about that now. Multiplicity has to do with the number of repeated zeros / x's. And what do I mean by that? I mean that we might, when we're trying to find our zeros, there might be zeros that are repeated. Like we might get the same answer multiple times. And if that's so, depending if we get that same answer 2 different times, 3 different times, or just 1 time, 4 times, well, once again, back to this idea of odd and even. If we have an odd number of multiplicity versus an even number of multiplicity, 2 things are going to happen. If it's an even number of multiplicity, at that particular zero, meaning at that x-intercept, you're going to have that it points in the same direction. It doesn't actually it does intersect the graph, but it doesn't pass through the x-axis. So this could also happen from above, or like I'm showing here, from below. But at that particular point, 0, if there's multiple versions of that 0, but multiple by 2, 4, 6 times, it's going to point in the same direction. Versus if it's an odd multiplicity, they're going to point in opposite directions. Meaning at that particular x-intercept, you're going to cross the x-axis to be able to point in the opposite direction. And when it comes to these zeros, there's something known as the fundamental theorem of algebra, that the number of zeros in a polynomial, in other words, the degree of a polynomial, given by the degree of the polynomial. So you know how many zeros you have based on the degree. So the degree tells you how many zeros you're going to have. Now, let's jump right into it. So here's a graph that we're going to sketch. Now, it doesn't look like this polynomial written in descending order. And that's because it's already in this second part of step 1. That it already set it equal to 0. Or we're going to set it equal to 0, right? That's our first step. So this is going to be equal to 0. And you would normally use factoring to help you find those zeros. But this is already factored for you, right? This says that there's this x squared just means x times x. So they're the same exact x. I only need to check one once. Now, why am I setting equal to 0? Well, you have to remember, when it comes to factoring, there's something known as a zero factor property, which means if a times b, remember, factors are separated by multiplication. Terms are separated by plus or minus signs. But once you have your polynomial factored, you can take each factor and set it equal to 0. Once you're done doing that, each one of those factors will give you a value for x, and that creates your x-intercept, or what we call our zeros. Now, hopefully you reviewed chapter 1, and you had practice with factoring by GCF, factoring by grouping, that's when you have 4 terms. A quadratic, that's when you have 3 terms, so this is also known as trinomial factoring. And then there's our special factors, right? Our binomial factoring, where there's a difference of squares, difference of cubes, sum of cubes. And those are very specific 2 terms of polynomials to factor. But here, this is factored for us. If you notice, everything is multiplying. So all I need to do is take one of these 2 x's and set it equal to 0. Then I take this factor, even though it's a bigger one. I'm just going to take that factor, set it equal to 0. And then once again, this particular factor, because of the square, remember this means x plus 5 times x plus 5. So we're saying there's 2 identical factors. So I don't need to write both equal to 0. I just need to write one of them equal to 0. Now this first one's already done because there's no other way to solve it. But we do have to say it has a multiplicity. It has a multiplicity of 2 because there was 2 of them. I just wrote one of them. This next one gives us x equals 2, which this has a multiplicity. I'm just going to put multiplicity of 1 because there was only one factor that gave us this 2. And this next one is going to be x equals negative 5. And that's because this has a multiplicity of 2 because it was 2 of them. So you know I only wrote 1, there was 2 of these. So I mean something special is going to happen at these particular zeros. So like I said, we can just sketch them now. Right? I said once you find your zeros, the next step is to plot them. So how do we plot them? Again, even though this says x equals negative 5, this technically means negative 5 comma 0. This means 2 comma 0. And this one means 0 comma 0. Because these zeros are x-intercepts. So I can plot them. So at 0, 0, so 1 here. At 2 zeros here. And at negative 5 and 0. Now this is where we have to look. Even though this is not written in descending order, if all this was distributed, you would have a power of 2 here. When it gets multiplied with this x, you'll have a power of 3. And then this x, because it's x plus 5 times x plus 5, it's going to have a square in it. This square times this 1 is going to be a cube, but then times this other square, it's going to be to the 5th power. If you were to distribute all this and make it into this form of the polynomial, because of all these powers here, square times 1 times a linear times another square, you add those powers together. So the 1, the 2, the 1, and the 2, that's going to give us a degree of 5. And if it's a degree 5, that means it has an odd end behavior. And if you look at the leading coefficient, it's a positive 1. So that means I'm going to have, it's going to go up on the right and down on the left. But what's going to happen to these points? Well, that's where the multiplicity comes into play. Because at negative 5, I have an even multiplicity. So that tells me I am not going to intersect. I'm intersecting the x-axis, but I'm not crossing through to the other side. It's just going to point in the same direction that the end behavior is pointing. But at this 0, have a multiplicity of 1. That's odd. So that's how I know it's going to go through that 0. And at 2, oh, sorry, I take that back. At 0, right, this was 0. I got mixed up with the points. This is this point here at 0. It has a multiplicity of 2, so I was wrong. It actually touches that point, and then comes back down again, because the even multiplicity never crosses through to the other side of the x-axis. But at this 2, it's an odd multiplicity, so that means it has to go through. And to be able to match with my end behavior, I needed to go through as well. And that's how we can quickly sketch. Now, is this a exact replica of the graph. No, this might go down a lot more. This might not go down as much. This could go really far down. But I'm not looking for that precision. I'm looking for the understanding of this example, how it flattens out near that point, comes back down, flattens out and touches it, and then finally goes through the next point. Now let's try another example. This one again is also nicely factored for us. And just like the last one, there's already two factors here. I only need to use one of them, but I need to make sure that I write that this has a multiplicity of 2 because there's two of them. Now these next ones are pretty straightforward. It's x plus 2 equals 0. That's going to be x is equal to negative 2. The next one is x minus 4 equals 0. It's going to be x is equal to positive 4. And both of these have a multiplicity of 1. Multiplicity of 1. And because of that, it's going to tell us something about our graph at these points. So these are intercepts. So this is going to be 0, 0, 0 again. This is going to be negative 2, 0. This is going to be 4, 0. And then we can plot all these points. So here at 0, 0, negative 2, 0, and 4, 0. And once again, this has a power of 2, power of 1, power of 1. If I add all these powers, that's going to be a degree 4. So that means, and the leading coefficient is positive again. So I know it's going to go up on the right and up on the left. And at this negative 2, I have a multiplicity of 1. That's an odd multiplicity. So I know I'm going to go through that point. I'm going to go through that point. And then at this 0, 0, it has a multiplicity of 2. That's an even multiplicity. So that means I can't go through. I do intersect it, but I have to come back. And at 4, it has an odd multiplicity. So I know I'm going to go through, which once again makes sense because it matches the end behavior. Now, like I said, this could be going much further down. So can this. And if you want to figure out exactly how far down this goes, choose one of these points. You have 1, 2, 3, 4, negative 1, negative 2. You can choose, for example, 2. Plug it into your function. And that's going to give you your y value to know exactly how far down to go. Same thing with this negative 1. Let me just do it because it's a nice number. If I plug in negative 1, that's going to be negative 1 squared, negative 1 plus 2, and then negative 1 minus 4. That simplifies to 1 times 1 times negative 5. And that's going to give me a 5. So really, this is 1, 2, 3, 4, 5. So this graph actually goes much further down and then comes back up. But I'm not looking for that type of precision. I want a rough understanding of what the graph looks like. Now, here, I skipped a step on this last one. I didn't actually set this equal to 0. But on this next one, I'm going to have to set it equal to 0. Because it's not as simple as just taking each factor and setting them equal to 0 because it's not in a factored form. But there's something I can already just from the beginning take away. That the leading coefficient is negative and the degree is odd. So that tells me that the end behavior It's going to point up on the left, down on the right. But we can get to that once we sketch it. But to take care of that leading coefficient, I'm going to factor that negative out of each term. And remember I said by the factoring, that was my GCF. So if you see a coefficient, you're going to factor it out for these polynomials. Whether that be a negative or some other number, you want to factor it out. And if you notice, we have 1, 2, 3, 4 terms. So we're going to factor by grouping. And if you review chapter 1, this is how you factor by grouping. You take the first two, and then you take the second two. Now, even though I'm writing these brackets, this does not mean multiplication. This was 4 terms, it's still 4 terms. But this method calls for this type of brackets. So I'm still have my negative. Don't forget that negative. Nothing has changed. But factor by grouping means I need to find the GCF of the first 2 terms, which they don't have any numbers in common, but they do have variables. I can factor out an x squared. That leaves me with x plus 4. And I can factor out a negative 1, which leaves me with x plus 4. And the goal to factor by grouping is to be left with something along these lines where there's 2 identical factors. And now remember that none of these were multiplying. This is still adding or subtracting. But the fact that these 2 are the same in each term, once again, I can go back to using my GCF. Factor out that x plus 4. And then I'm left with these 2 terms in here. X squared minus 1. And hopefully remember that x squared minus 1 is the difference of squares, which is x plus 1, x minus 1. Right? This comes from the formula of the difference of squares. Let me make a quick note. A squared minus b squared is equal to a plus b, a minus b. You always use that to save you some time. But now that I have everything factored, I can set each factor, so x plus 4. Or for the sake of time, I know this x plus 4, once I set it equal to 0, is going to give me a negative 4. This next one's going to give me a negative 1. And the last one's going to give me a positive 1. Now, they all have a multiplicity of 1. Because they didn't appear any more times. So if I plot this, I have my negative 4. I have my negative 1, my positive 1. And because it's an odd and a negative leading coefficient, it goes up on the right. Sorry, up on the left, down on the right. And that's what our NB here showed us. For an odd degree, negative leading coefficient, up on the right, down on the left. And then multiplicity at this negative 4 is 1. So we're going to go through. At negative 1, it's also 1, so we're going to go through. And at positive 1, it's 1, so we're going to go through. And once again, if you wanted to verify how far down or how far up these go, you can just plug it in. So really quickly, since it's a nice number, I'll do P of 0, which is negative 0 cubed minus 4 times 0 squared plus 0 plus 4, which the 0 cancel, that cancel, that cancels. We're left with 4. So technically, this middle part should have gone up to 4 and come back down. But I'm not looking for that precision. I'm looking for a rough understanding of this graph. And that's factoring by grouping here. Here's another problem that we set equal to 0 first. And how do we handle this? Just like the last one, we want to start by thinking, is there a GCF? Which in here there is. The numbers, if you notice, all have a 4 in them of some kind. So I'll be able to factor out a 4. And they all have at least 3 x's. This has 5, this has 4, this has 3, so I can factor out 3 out of each one. That will then leave me with x squared plus 2x plus 1. Remember what I said before. Because my GCF is this entire last term, there's always that 1 that's there. Because if you distribute this back, you want to be able to get that third term. Now we have to recall, how do we factor this? Well, I like using this diamond/x method, which takes the leading coefficient and the constant coefficient and multiplies them, which is going to be 1. And then it takes the middle term, puts it here at the bottom. And then I need to find two numbers that multiply to 1, but add up to 2. And the only thing that multiplies to 1 is 1. So 1 times 1 is 1, but 1 plus 1 is 2. Now, because they're both positive, I like going directly into my factors. So that's going to be 4x cubed. And this is the trick that I use for factoring trinomials. I'm going to take x plus 1, and then x plus 1. And normally, I would then take the leading coefficient and divide these two constants. But because it's 1, 1's going to divide these perfectly. So I don't need to do anything other than that. This is how you would factor that trinomial. You find your two numbers, you rewrite your factors. If whatever your coefficient is, you divide these two constants. And if it didn't divide it, if that coefficient was not able to divide these two constants, I would just write it in front as a coefficient of the x inside these factors. And that works great. And once again, this says x cubed, meaning there's 3 of them. I only need to write 1. And that 4 isn't going to change my answer when I set things equal to 0. Because if there was a 4, I would just divide the 4 over, and that would give me 0. But this has a multiplicity of 3 because there are 3 of them. And I'm only going to write one of these x plus 1s, which will give me x is equal to negative 1. But this has a multiplicity of 2 because there is 2 of them. Now, and if you're asking, wait, didn't you say the fundamental theorem of algebra said that the degree of the polynomial gives us how many zeros we have? And that's true. So 5, that means this looks like there's only 2, but there's 3 here and 2 here. That makes a total of 5 zeros. So then our x-intercepts. So once again, this is 0, 0. This is negative 1, comma 0. So there's a point here and a point here. And if the degree is odd with a positive coefficient, it's going to go up on the right, down on the left. And then at negative 1, we have an even multiplicity. So that means I'm not going to cross. I'm going to come back down. But then at 0, I have to go through because it is an odd multiplicity at that origin. So we go through, which makes sense because it matches up with my end behavior. Now one more. And at any moment you can pause and try any of these, rewind and revisit. But once again, you set it equal to 0. Remember, whatever the coefficient is, they don't have other numbers in common, but that negative, you can always factor it out. This has 4 x's, 3 and 2. So I can take 2 out of each one of them, leaving me with x squared plus 3x minus 2, since I didn't factor out that 2. But once again, I like using my x/diamond method, or whatever you call it. There's going to be a 1 here, times the constant coefficient is negative 2. The middle term is 3. And for two numbers to multiply to 3, multiply to -2, but add up to 3, we have to think of what numbers will work. So if you're looking at these, if you notice, it's not working, right? There's no way of doing this. And the mistake I made is I did factor out the negative, but I did not take it out of each term. This is supposed to be negative, and this one's supposed to be positive. So when you go too quick, you want to be careful to make those small mistakes. I factored out the negative out of each term, but I still wrote this positive and this one negative. So that changes things up because this is going to be positive, and then this one's going to be negative. Which now this, we know, is -1, -1, and -2. Because -1 times -2 is +2. But -1 plus -1 is -3. And like I said, you would just keep writing this -x squared, but you take those two numbers, x minus 1, x minus 2, and because the loading, I would normally take the leading coefficient inside of these brackets and divide these two constants, which we can, but dividing by 1 is going to keep everything the same. If they didn't divide, then I would write it in front. So that would leave me with, once again, I would set that first one equal to 0. That negative isn't going to do anything. The square, there's two of them. I'm only going to write 1. But I need to make sure I write multiplicity of 2. This is going to give me -1 with a multiplicity of 1. And then this, that's going to give me +1. And this is going to be +2, right? This one, this one, this one. Also with the multiplicity of 1. If I plot my zeros, I have 1 at 0, 0. 1, 1, 1 comma 0, and 2 comma 0. And if we look again, it has an even multiplicity, or even degree, and a negative leading coefficient. So they both face down. If you guys remember from transformations, that negative makes a reflection on the x-axis. That's why they're facing downward. Now at 0 has an even multiplicity, so that means it's going to come back down. And then the other ones have odd multiplicity, so it's going to go through and then through, which makes sense because it's matching up with the end behavior. So even multiplicity, you just touch the graph. Odd, you go through. Odd, you go through. And that's, again, the main thing is really knowing how to factor. Now we eventually will talk about this last method on the next video. But practice these, redo them, try them, see how they go.